All right, Kyle Munyon here to help you guys with lesson 3-2, conditional statements. Let's go ahead and jump right in. So we have a couple of targets here. Identify a hypothesis and conclusion of a conditional statement. That's very important. Eventually, that's one of the test questions you'll definitely have for this week's quiz as well as the final. And know what a counterexample is and for false conditional statements. So we have a couple of different targets here. First, we need to know what a conditional statement is and then the different parts of it so that we'll be able to identify the hypothesis and conclusion and how to tell whether they're true or false. That's validating, determining whether they're true or false. All right, so rules of logic reasoning involve using a set of given statements along with a valid argument to reach conclusion. In the last segment, we used deductive reasoning to give valid reasons to be able to prove something. Here, we're going to be using conditional statements. That is any statement that can be written in the form if, then. So if, hypothesis, then conclusion. For example, if it rains tomorrow, then I will bring an umbrella. That is a conditional statement because it is in the form if, then. All right, so obviously in terms of math, we could have statement if 3 parentheses x plus 2 minus 1 equals 5x plus 11, then x equals negative 3. So you have a hypothesis and a conclusion. That is a conditional statement because it is in the form if, then, and we can identify the hypothesis as anything after the word if, and the conclusion as anything after the word then. So using these underlines and boxes, I'm going to be identifying the hypothesis and conclusion. So it says use the conditional statement, try this A down here, use the conditional statement if x plus 7 equals 10, then x equals 3. What is the hypothesis? That is the hypothesis. And what is the conclusion? The conclusion is everything after the word then, so that is the conclusion. So the hypothesis is x plus 7 equals 10. The conclusion is x equals 3. You'll notice I did not include the word if as part of the hypothesis. It's everything after if, and then is not part of the conclusion. It's anything after the word then for the conclusion. State the property of equality that justifies the conclusion. So just like in the last one, we would need to justify some of these. If you were to subtract 7 from both sides, so subtraction property of equality. Oops. All right, so continuing with this one, we can actually substitute P's and Q's to help us identify the hypothesis and conclusion. So from this point forward, I may represent the hypothesis with the letter P and the conclusion with the letter Q. So for a hypothesis, we could use P, and for the conclusion, I could use Q. So restate each conditional statement in if-then form. You'll notice here that there's lots of different ways that we could write conditional statements here. All of these are considered conditional statements because they could be written in the form if P, then Q. So restate each conditional statement in if-then form. I'll go if you go. So if you go, then I'll go. So okay, so now this is in the form if you go, then I'll go. It is in the form if then, so that definitely is a conditional statement. Here, there is smoke only if there is fire. I notice that's exactly like this example over here. So if there is smoke, then there is fire. This is an if-then form now, and notice P only if Q, so P only if Q. Whoops, I guess it'd be the whole thing there. So P right here, there is smoke. So if there is smoke, then there is fire. So I still have the same hypothesis and conclusion. I just wrote it in the form if then. Last one I see, I'm going to get rid of some of this just because it's kind of getting in the way. I'll use a different color here. It says x equals 4 implies x squared equals 16. That looks a lot like, whoops, not that one, this one here. So P implies Q. So this is my hypothesis P. This is my conclusion Q. So I can write it if, whoops, P, then Q. So if x equals 4, then x squared equals 16. All right, so notice here, I do have my hypothesis and my conclusion on there, just like it's supposed to on the examples. All right, moving on, we can learn now what a counterexample is. So an if-then statement is only considered false if the hypothesis is true and the conclusion is false. What does that mean? So remember that example where I said, hey, if it rains tomorrow, then I'll bring an umbrella? Well, let's say tomorrow I show up and you see me and I don't have an umbrella and you're like, hey, you lied. Well, I would only be lying if it rained and I did not have an umbrella. If it doesn't rain, then the hypothesis was never met. We can't even test the conclusion because the first part wasn't even met. So to have a conditional statement that's false, you need to meet the condition of the hypothesis. So that part has to be true, and then you can test the conclusion. And it's either will make it false or true. If you're using examples that don't even meet the hypothesis, you can't test that conditional statement. You can't come up with counterexamples. Obviously, let's do some here, make sure we know what we're doing. This is a false conditional statement. Identify the hypothesis, conclusion, and then give a counterexample. All right, so it says if two numbers are odd, we'll go ahead and identify the hypothesis there, then their sum is odd. All right, so we have our hypothesis P. I'm not going to write it down again. That's our hypothesis. Two numbers are odd. Their conclusion is their sum is odd. Give a counterexample. So how do we do that? We need to meet the hypothesis. So think of two numbers that are odd, 1 and 3. Okay, so did I meet the hypothesis? Two numbers are odd? Check. Now I can test the conclusion. Then their sum is odd. Okay, well, there's an example that proves this statement is false because the numbers I came up with meet the hypothesis, but then the conclusion is not met that says their sum is supposed to be odd. 4 is obviously not odd. So this would be a counterexample. 1 and 3 is a counterexample for this statement. Okay, so let's take a moment and try questions 3 through 7. I'd like you guys to try these on your own, so please take a moment, pause the video now. When you resume the video, I'll go through the answers. You can check your work. All right, hopefully you have taken a moment to try and answer some of these. If you got stuck, we're going through the answers now to see where you got stuck at, and hopefully you'll have some better understanding before you do the homework practice. Number 3 says if you can find an example for which both the hypothesis and the conclusion of a conditional statement are true, is the conditional statement itself necessarily true? Explain. So this one's an interesting one. If you find an example where the hypothesis and the conclusion of a conditional statement are both true, you have found one example that's true. Doesn't mean the conditional statement for that is true. So explain. Easiest way to do that would be like with an example. So let's say if a number is squared, then it is positive. So I could come up with an example that's true. If a number is squared, then the result is positive, like 3. If I square 3, I get 9. the result is positive. Great. Does that mean that that's a true statement? No, that's just one example that's true. Doesn't make the statement true. It's only true if there are no counterexamples. So you think of every possible number that you can think of and see if there's any counterexamples. For this one, there is a counterexample if you were to use 0. So 0 squared equals 0, and 0 is not positive. So that is a counterexample. Even though I had an example 3 squared is 9 that was true, the hypothesis was true, I picked a number, and when I squared it, it was positive. There was a counterexample, so that doesn't make it true just because there was one example that was. Number 4. I guess I could answer this one. If there are no counterexamples. All right, number 4 says give an example of a true conditional statement that includes this hypothesis. So if an angle is named ABC, so obviously we'd have to meet that one for it to be true, then what could you say? So if you have an angle named ABC, remember, it has to go in order. B would have to be in the middle, so you could say that's your conclusion right there if you wanted to. You could say B is the vertex of the angle. If you have an angle named ABC, then B is the vertex of that angle. You could also say if you have an angle named ABC, then points A and C have to be on the two opposite legs of that angle. They obviously can't be points on the same side. I'm just going to go with then B is the vertex. That's an easy one. All right, number 5, give an example of a true conditional statement that includes this conclusion. The angles share a vertex. So we have to end up with angles sharing a vertex. So the easiest way to do this would be just draw a vertex and then make two separate angles. I happen to make a linear pair down here. So I could say something along the lines of if two angles are a linear pair, then they have to share a vertex. So that would be an easy one. It's a true conditional statement. If they're a linear pair, then the two angles that make that linear pair do have to share a vertex. So if this was the conclusion, so P could be if two angles form a linear pair. Whoops. All right. And remember, it's everything after the word if. So if two angles form a linear pair. A common mistake on this one, students might have come up with something like, if two angles are complementary, then they share a vertex. It doesn't have to be true, because you could draw any two angles that don't share a vertex, and if they add up to 90 degrees, they're still complementary. They don't have to share a vertex. So that would not necessarily have been a true conditional statement if you said if two angles are complementary or if two angles are supplementary. But specifically, I made them a linear pair, which by definition they have to be adjacent to each other to share a vertex. You could have just said if two angles are adjacent, then they share a vertex. Would have been another easy one you could have used. All right. For the next one, number 6. Caesar conjectures, makes a statement that he believes to be true, that the quotient of any two even numbers greater than 0 is odd. Quotient means divide. So any two numbers greater than 0. Write Caesar's conjecture as a conditional statement. If you take any two numbers that are greater than 0, then their quotient is odd. Oops. Okay, so part A, we have a conditional statement. Part B is give a counterexample. So think of two numbers that are greater than 0. And whoops, it's supposed to be even. I guess that's part of it. Should throw that in there. So any two even numbers, I guess we have to use even numbers to meet the hypothesis. So 2, 4, 6, 8, any of those. Then their quotient is odd. So I don't know, 2 and 4. What's the quotient of 2 and 4? 2 divided by 4 is 1/2. 1/2 is not an odd number. You could make it really easy if you want to do something odd. You could say like 12 and 6. 12 divided by 6 is 2. That's not odd. So example, 12 and 6, because 12 divided by 6 equals 2, and that's not odd. So you pick two even numbers greater than 0. When you divided them, you get an even number, not an odd number. Write the definition, number 7. Write the definition of collinear points as a conditional statement. So for number 7, remember collinear points are points that lie on the same line. So if two or more points lie on the same line, then they are collinear. I always forget if it's lie or lay. Who knows? Lay on the same line. All right. So I think that concludes the lesson part. I will give you a moment here to stop and try questions 8 through 12 as additional practice. I'll be back in just a second and you can restart the video and I'll go over 8 through 12. All right. Now hopefully you've tried questions 8 through 12. Let's go over and check our answers on these. Write the statement in if-then form. Two angles that add up to 90 degrees only if they are complements of each other. Only if they are complements of each other. So if you go back a couple of pages and look at the notes, one of the examples that we had was P only if Q. So I know the part here is P, the hypothesis, and the part here is conclusion. So I have P, my hypothesis, only if Q, the conclusion. So write it in if-then form. If two angles have measure that add up to 90, then they are complements of each other. I give up. Then they are complements of each other. I think you guys get the gist of this writing that one. For number 9, it says, which of the following is a counter example of the statement? So we need to find an example that meets the hypothesis and then when we test the conclusion is false. So it says if an angle is acute, then it measures 80 degrees. So question or answer choice A doesn't even meet the hypothesis. Not an acute angle. Has to be between 0 and 90. Same thing. 90 is not an acute angle, so it doesn't even meet the hypothesis. Can't be a counterexample. 80 and 70 are both acute angles, so both of these meet the hypothesis. Problem with this one is it does also meet the conclusion, so that would actually work against us. We're trying to find a counterexample. That one says, oh, if an angle is acute, then it's 80. Well, this one is 80. But this one is an acute angle that's not 80, so this one would be our counterexample. It meets the hypothesis, and then when we test the conclusion, it's false. That is a counterexample. For number 10, identify the hypothesis and conclusion of this statement. Pretty easy at this point, I think. Hypothesis is this part right here, everything after the word if. The conclusion is this part right here, everything after the word then, and we can use P and Q to identify the hypothesis and conclusion. All right, last two that we have, question 11 and 12. Joanna says that 4 plus 7 equals 11 is a counterexample to the following conditional statement. Is she correct? If two integers are even, then their sum is odd. She is incorrect because the hypothesis is not met. Right there. Are the two integers that she picked even? Nope. So she didn't even meet the hypothesis, so you can't test the conclusion to see if it's a counterexample. That's the error that she made on this one. You don't even need to read the conclusion. I already know it's not a counterexample because she didn't meet the hypothesis. For number 12, why do you only need a single counterexample to show that a conditional statement is false? I mean, that's because if you have an example that proves it's false, why do you only need one? Well, because that's all that's required. I'm sure there's a better explanation, but all you need is one counterexample to prove that's false. All right, that does conclude 3-2. Hopefully you've already done 3-1. There is one more lesson, 3-3. Once you get done with those, you should be able to do the activity 3 practice listed in your homework. That would be at the end. It's actually at the end of this section if you have the PDF pulled up.